So the first thing we have is we have a table here. It says water is pumped into a tank at a rate modeled by W of t equals 2000 e to the negative t squared over 20 liters per hour for 0 less than t less than 8 hours, where t is measured in hours. Water is removed from the tank given by this table here. And so we have selected times, and we need to estimate r prime of 2. Remember, the idea here is that we're using the fact that the average rate of change is a very good approximation for the instantaneous rate of change. So what we can do is we can say that r prime of 2 is approximately equal to r of 3 minus r of 1 over 3 minus 1. So I could say this is 950 minus 1190 over 3 minus 1. And I can leave my answer like this, but I need to make sure that I put liters per hour squared, because this is a change in rate over time. So it's liters per hour every hour that we've got here. And so this ends up being our answer. For part B, it says use a left Riemann sum with the 4 subintervals indicated by the table to estimate the total amount of water removed in the tank during the 8 hours. And then the question is this an overestimate or an underestimate of the total amount removed, and to give a reason. So if I'm going to do an integral from 0 to 8 of r of t dt, I can use a Riemann sum to approximate this, and I'm using a left Riemann sum, which means I'm going to be using this endpoint on the domain from 0 to 1. I'm going to be using this endpoint from 1 to 3, this endpoint from 3 to 6, and this endpoint from 6 to 8. So I've got a width of 1 for my first rectangle, so 1 times 1340, plus this is going to be a width of 2 for this next rectangle using the left endpoint of 1190, and a width of 3 for this rectangle at 950, and a width of 2 at this rectangle, which is going to be 740. And so this would be a good approximation of this. Keep in mind that I'm integrating a rate over time, so this is going to be liters. And again, because they gave us units, it's going to be a good idea to make sure that we have units in our answer. And I need to make sure I answer the other part of the question: is this an overestimate or an underestimate? Notice that we know that our function is decreasing. So if I'm using a decreasing function and a left Riemann sum, because I'm using the left endpoint, my left Riemann sum will have all of this, which is extra, not part of the area under the curve. And so that means that for a decreasing function, a left Riemann sum is going to be an overestimate. So because r of t is decreasing on the interval 0, 8, the left Riemann sum is an overestimate. So notice here, to get the full credit, I need to have my approximation, I need to have that it's an overestimate, and I need to have my justification because r of t is decreasing on that interval. So what we're going to do is add this up. So we're going to have 1340 plus 2 times 1190 plus 3 times 950 plus 2 times 740. And again, the only reason that I'm doing this is because on the next problem, I'm going to need this value of 8050. So I'm going to use this value on the next problem. So going on to the next part, it says use the answer for part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Keep in mind that the total water is going to equal the total amount in minus the total amount out. So looking at this, I'm going to have to do the integral from 0 to 8 of the function they give us, w of t dt, minus the total amount out, which we just calculated to be 8050 liters. So again, I'm going to go back to my calculator, and I want to find the integral of w of t, which is 2000 e to the t squared divided by 20 with respect to t from 0 to 8, and I get 76,701 minus 8,000, which is going to give us the number of liters that we've got at the end of part C here. Okay. So on to part D, it says for 0 less than t less than 8, is there a time t where the rate at which the water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. Now, the key here is that r of t is going to be a continuous decreasing function, and w is going to be a continuous increasing function. And because of continuity, there's going to have to be some point at which these 2 points intersect. So my justification for this is the intermediate value theorem. So the thing is, because r of t is continuous on the interval from 0 to 8, r of t attains every value in the range from 700 to 1340. And similarly, because w of t is continuous on the domain 0 to 8, then w of t attains every value on the domain from, it's going to be from 2000 to whatever e to the negative 64 over 20 is, which is going to be something very close to e cubed. So, but the idea here is that because we attain every value on this range and every value on this range, because the ranges intersect, there is at least one t where w of t equals r of t. So that's our justification here, and of course the tool that we're using here is this intermediate value theorem. The intermediate value theorem is what allows me to justify that I actually hit every point in here. So I really should say by the intermediate value theorem, and this is true by the intermediate value theorem as well.